Hello, welcome to another episode of Beam There Done That. I'm your host, one of your hosts, Alan Wyma, and today I have Francesco Cesarini.
You have me with you every day. Hi, Alan. Hi, I'm Francesco. I'm also co-host. And today we're returning to the conversation we started a couple of months ago. Our guest is again, Björn Gustafsson, the B in the Beam. He's the member of the OTP team. He's a member of the OTP team since 1996 and actually the person who shepherded the Beam virtual machine through every major transition it has been through, starting from when he took it over from Bogdan, the other B in the Beam. So last time we sat down with Björn, we were talking about native records, so the first new Erlang data type in over a decade. Today, we want to go much broader. We want to go into the Beam itself. Where did it come from? How did it become what it is now? And what comes next. Welcome back, Björn. I'd say
Thank you.
most engineers who work on language runtimes spend their careers building one, and you've helped build this one through its every era, through every year it's had, and and that's not a career. I think many say it's an institution. So why don't you just take a minute to tell the listeners, particularly the new ones who didn't listen to the Native Records episode, what you've actually spent the last 30 years doing.
Okay, thank you. Yeah, so I started at the OTP team in December of 1996. I think I started working on the Windows 95 port of Jam, actually, the other machine. But I soon started to work with the Beam, I think in 1997. So worked with that long time, and also with the compiler, and done yeah. Uh, that's mostly what I've done. Other things in runtime system, so on, but it's mostly the Beam and its compiler.
Before we get into the Beam, I'm kind of curious. I mean, 30 years working on the Beam itself, and of course in the Erlang ecosystem, there must be some kind of bug or series of bugs that have kind of haunted you for a while and really kind of affected your life. Could be in a positive way, could be in a negative way. Do you have any kind of memory of something like this?
Actually, I think there's one bug in particular. And it's a bug in the Erlang compiler, and it caused random crashes in the runtime system sometimes. And there was another member of our team that spent several weeks hunting it down. We didn't know that it was in compiler, but he found the bug in the runtime system running debuggers and so on. So that was a little bit embarrassing for me. So I decided to write a pass in the compiler that would check the Beam code so that was correct. It couldn't cause this kind of problem. For example, so it didn't try to access a Beam register that contained garbage. So now we have that pass in the Beam in the compiler. It's called the BEAM Validator.
I think there are many, many compiler bugs which, yeah, which I remember, which come to mind where, things have to be validated. Let's see if some other ones come up, in our calls today. But let's start off by giving our listeners some background, before we get into what the Beam is today. Most people listening think of, the Erlang virtual machine as a single VM. But, when I was at the computer science lab and also when you joined, there were three virtual machines being built in parallel, each by a different person, and they were all experimenting with different approaches. I mean, when you and I started with Erlang, we had the Jam, which was, Joe's abstract machine, which was the VM, which was prevalently used in production. I don't think many listeners will have heard about the Virding's Erlang emulator, which I believe, when I was at the lab, had just been mothballed. I asked Robert, he didn't remember the exact date when it got retired. And then we had the Beam, which was Bogdan's Erlang abstract machine. And what the Beam did is it compiled Erlang to C and Erlang to C, and it could also run existing Beam code. Can you walk us through very briefly these three different VMs?
Yes. we have the JAM Joe's abstract machine, as you said, and it was designed by Joe Armstrong, but the runtime system was implemented by Mike Williams. So it was a bytecode interpreter, written as a pretty basic one, but it turned out to be too slow. They wanted to have something much faster. So then Robert Virding built his own V, and he worked on it alone. I don't think he ever showed it to someone to actually use it. It had a global heap for all processes. So it was faster at message passing, and it was faster than JAM at the time. But it was before RAM got slower than CPU. So then CPUs needed to use caches to keep up performance. Then we didn't get any faster because it had a bad a cache hit rate because of the global shared heap. So I think that's why he stopped maintaining it. I think we'll hear a little bit more of it later, I think. And then we have the BEAM. It started out as Turbo Erlang, and the name didn't really fly. Well, the first version would compile the entire Erlang application to C code, and then that had to be compiled, and then would be one huge executable. It was in very slow compilation time to try for real applications. So it was not really practical, but it was faster than JAM, of course. Then the next generation, the Bogdan worked was, he called it BEAM, and was Bogdan's Erlang abstract machine, I think. So here, each module could be compiled separately, either to C code, and the C code would be turned into a shared library, or it could be compiled into bytecode for the BEAM machine. So there was an interpreter that could execute the BEAM code, but it didn't execute the bytecode directly. There was a loader, handwritten, that would translate each instruction into a form that's most suitable for fast execution. Something's called threaded code, something that's used by language called fault also. So even this BEAM machine was faster than JAM, even if they didn't compile to C. So the idea was that you could mix, if you have time-critical code, you could compile that to C code, and other parts of the system not that time-critical could be compiled to BEAM code to preserve memory, because the C code was huge. Yes, I
It
think
was almost like a it was code explosion, which happened.
Yes. And that was the state of BEAM when I started working in 1997. That was working. So you could load, it works just like you could do hot code loading, and you could decide whether you want to have each module compiled to via C or to the BEAM machine.
I remember also the actual execution of the code itself for sequential code was 10 to 20 times faster than on the jam, so it was a huge increase in performance. But as soon as you started running concurrent programs, apart from the code explosion, which caused huge issues, I mean, in the embedded systems, I think hard drives were really, really expensive back then. The problem was you didn't get this 10x speed execution. Erlang programs at the time were concurrent. The real value was concurrency, lots of processes interacting with each other. And if I remember correctly, the actual speed increase when you started taking concurrency in mind was just 2x. So the 10 to 20x disappeared and it became 2x. Do I remember correctly?
Yes, and I think some reason why it didn't get the speed, because the code was huge, so that would make it slower it will not fit, all will not fit into the cache, in the either code cache or data cache. So that is one reason. And another reason is, of course, as you said, concurrency. When you're sending messages to other processes, that is already written in C, so it didn't speed up message passing and so on. So it's only speeded up sequential parts of the code. And in a real telecom system, or it is not really that much sequential code that you could speed up.
Because I remember, I think we had exactly the same problem with, they designed an Erlang chip within Ericsson, and it was never released because, again, sequential code, became super fast. Concurrency, that became the main bottleneck. And, we had to explain, to the developer chip that, you need to start designing your chips with concurrency in mind. And obviously, this predated multicore. So just to make this sharp for the listener, sequential code on the Beam back then was much faster than the Jam. You compile to C, you ran native code, your big performance wins. Why didn't that win? Why aren't we all running Bogdan's Erlang abstract machine today?
In a way, we still are running it. So I took over maintenance of Beam when Bogdan left Ericsson in 1997, I think. So I started to improve it step by step, doing tiny refactoring, keeping it working all the time. I prefer to work that way, to always have something working. So that actually evolved to the Beam we have today. And we had a goal to make Beam a stable and maintainable, so that we could retire Jam and while still making this as fast as possible.
Is what you invented what is in use today, or were there compromises with, did you take over Bogdan's code? So Turbo Erlang, which then became, the first version of the Beam.
Yeah, so I took over Bogdan's code. So I'm not really an inventor. I didn't invent the Beam, and it shouldn't. If Bogdan hadn't invented it, there shouldn't be the Beam we have today. But I improved it. But I did one invention, I think, on my own, and that was to invent the Beam loader, and that is still in use today. So I didn't like. There was this kind of symbolic relationship between the compiler and runtime system. The compiler knew far too much about the runtime system and did a lot of optimization, which made the Beam instruction set very unwieldy, a lot of instructions, several hundreds. And because of the way the Beam machine worked, there had to be handwritten code in the loader to translate each instruction from the bytecode to the actual format when executed it. So I wanted to do something better. So I invented a new loader that could do that translation automatically. I had a Perl script that generated the C code. I didn't have to write that myself. So I could write in a specification language how the instructions should work, and could also do some optimizations, for example, to combine instructions. That is an important optimization. It can make it run same memory and run faster. So I wanted to move that to the runtime system, to the loader. Actually, I can show you an example of that to make that a little bit clearer. So here is an example combining Beam instructions. So we have this Erlang code, simple Erlang code, and then we have this sequence of two instructions. First, we have move instruction to move this intake 42 into an Beam register X0, and then we do a call. And the original Beam compiler used to combine these instructions, and it combined a lot of other instructions, did other visualizations of instructions. So I wanted to do all this in the loader, and the loader can now do this combination. When loading the code, it will combine it to new instructions that only exist in the runtime system. So with the help of this smarter loader, I could optimize the performance of the Beam machine, and that helped me to make the Beam machine faster than the C core, at least as fast in a real system. Maybe not in benchmarks, but in a real system. So it made the C version of Beam irrelevant. So we could rip out that code, and that was complicated code that was not very portable. We have to have 3 different versions for different of architecture. So we had for the Spark, Solaris Spark or Sun Spark, whatever. We have one version that was fastest, and then we have some other version that of Beam for generated Beam for C. For an interprocessor, it would not be as fast. It had to be generate more complicated code. So I really wanted to get rid of generating C code. So I was able to make the Beam emulator or interpreter fast enough.
So Bogdan's beam resulted in, how can we make sequential code faster, but more in like an academic, kind of setting, not necessarily in like a working kind of, like production instance kind of way. But you basically improved on his virtual machine to make Erlang actually run in a very rock solid way. Is that a good way to kind of wrap up about the original Bogdan's beam versus your beam?
Yes. So the goal was to make it possible to retire a gem, and we could do that a little bit later.
I remember being surprised when the OTP announced, there was very good progress on a new VM, which, we should start looking into using in production. So I was at Ericsson at the time, and and I was very, very conservative. So, we didn't jump, we didn't leave the jam and jump over to it. I'm trying to remember why I was surprised. Did you start on the Beam as a side project in your spare time, or was management aware and had actually asked you to start looking at a possible replacement for the jam?
At one time, we actually wanted to implement yet another Erlang machine with a new compiler written by Robert. He has written a new compiler for VE, for his Erlang, a better compiler. So we actually were thinking about writing a new implementation, and we had some discussion was Robert and you and Bogdan, I suppose, and Tony Rågvall and I, we were discussing. But we never started on it. And when Bogdan left, I was thinking, okay, I've already done quite a lot of work with Beam, because my boss asked me to help maintaining Beam while Bogdan was still working at Ericsson. I helped fixing bugs and doing other improvement. So I already done quite a lot at that time. I think, okay, the runtime system is okay as it is. So why not use the new compiler, use Robert's new compiler and adapt it for the existing Beam. So that's what I did.
We've been talking about, the virtual machines and also abstract machines. I'd like to kind of touch on 2 points, right? Is there a difference between a virtual machine and an abstract machine? And coming back to, we basically decided that, this is a virtual machine. What actually is a virtual machine?
So virtual machine can be a lot of things. It could be that you emulate a complete computer. We are not doing that in Beam. So Beam is just for executing Erlang programs. And I guess we call it an emulator. I think the reason for that was that we were thinking about creating actual hardware. So we thought about this machine as an emulator, emulating hardware. There were some attempts to create hardware, but they were never successful.
I'm also kind of curious about like the term abstract machine, right? Is that the same as a virtual machine?
Yes, in this context, yes. So yeah. We also nowadays call it interpreter. So we have different names for the Beam machine. Yeah.
The terminology which trips people up, you'll often hear the Erlang virtual machine and you'll hear the Beam. Are they the same thing? Are they different things? And what is the correct term we should be using?
Basically the same thing. I think we hear both.
Is the Atom VM on microcontrollers or the Ling VM, so the Erlang on Zen, also Erlang virtual machines?
Yes.
If we go back to the 90s, Björn and Bogdan's beam, won, and it became the production Erlang virtual machine. But the beam today isn't the beam that won back in the 90s. Why don't you walk us through what happened next? Let's go back to the 90s. I mean, I first used the beam, I think it was in 99, if I remember correctly. It was the AXD301 project. So it was the Ericsson's ATM switch, which is about 2 million lines of code and just had just gone into production. And I think they were the first project to actually use the beam in production. And I recall we
Yeah.
shipped the ANX project, so Ericsson's broadband solution with the Jam. And my very first experiences with the Beam was with the XE301's project. So it was Ericsson's foray into packet switching back in 99. It was an ATM switch. At that point in time, it was one of the very few times I saw the VM crash. When did the Jam, and that was the Beam VM because it was its very, very early days. When did the Jam actually get retired, and what made the team confident enough to bet, production telecom systems on the new Beam?
Yeah, so the last support release that supported Jam was OTP R5C, and at that time the Beam didn't support compiling to C anymore, and I've made a lot of bug fixes, clean up with the code, so we thought that was stable, as stable as Jam. So well, we didn't develop Jam for R6B.
R6, if I remember, was 2001, 2001, if I remember correctly, right?
Probably, I don't
Yeah,
remember.
yeah, yeah. I think it was a release per year. First release of OTP was in 96. So yeah, 2001, 2002, most likely. Yeah. So the biggest transition that Beam has been through is multi-core, and that was 2005, 2006. Can you walk us through it? When did it become a clear, single core? When did it become clear that the free lunch was over, that a single core, was a binding constraint?
Well, there had been some experiments to implement your multi-core or multi-CPU version of Erlang. I think Tony Rågvall was involved in one project with Pekka
Was
Hedqvist, I
Pekka
think.
Hedqvist. That is correct. That was 1996, 95, 96. He was doing his thesis project, alongside me at the lab. Actually, the machine they used was called Four Roses.
Oh,
Every
yes,
every
yes,
every yeah, every machine they had at the computer science lab was called after some form of alcohol, if I remember correctly.
yes. But that version of Jam was not compatible with the ordinary version of Jam because he had to redo the instruction set. I think I mentioned that the instruction set was all instructions were used in Jam, so there was no way to actually extend the Jam. So they implemented in a incompatible version of Jam, and we never did use that implementation. But we were thinking about it. It was getting more and more relevant to be able to run on multiple CPUs or on multiple cores. So at least from the beginning of the 2000s, we were thinking about it. It made it into OTP R11B, and I suppose it was started in 2005, 1 year before, and Rikard Gren did most of the work doing that. And Mikael Pettersson from the Hype team, the high performance high performance Erlang team, made some assembly routines to implement locking in an efficient way, because we had to have locks to protect things when multiple threads were running. So a basic version of SNP support that we called that time was released in 2006 in OTP R11B.
So for the listener, Erlang code was basically already concurrent. So what was actually single-threaded underneath?
We had our own Erlang scheduler that did all scheduling, and Erlang was designed to do what is called cooperative multitasking. That is, it will schedule out from one process to another only at certain points where we can save as little state as possible. A modern operating system kernel will need to save a lot more state because it can interrupt the current running thread at any point. So we can be a lot more efficient saving less state because Erlang is designed that way. Or after a certain number of functions, called say several thousand, it will save its state and move on to another process. So we only used one thread internally in the Erlang runtime system before the SMP runtime system.
What made this hard? Couldn't you just run the existing scheduler on every core?
Yes, we actually did run the scheduler on every core, but that meant that we have to have a global queue of processes waiting to be run, and that would have to be protected by a lock. So, and there were a lot of other things that had to be protected by locks so that multiple processes couldn't access them at once. So basically what Rika did was to add locking to many places in the runtime system. I think he did it in about a year. So we got basic version working.
Wasn't the goal to try to get the whole virtual machine to become completely lock-free? I know Kostis Dagonas was doing quite a bit of work around, so the bottlenecks, started coming in every place there were locks, and one of them, being ETS tables, for example. Kostis Dagonas started working on a lock-free ETS table. Was there was the goal, to make the whole VM lock-free?
No, not to make a lock free. That is probably impossible. We wanted to have better performance. So we wanted to have more fine-grained locks. For one example, the IO system, IO to files, the screen and so on, was protected by single lock. So if two processes route to two different files, one process would have to wait for another because the first process would take the lock and no other process could do IO. So we gradually added more fine-grained locks, so we didn't have to lock the entire runtime system. So for example, we made it possible to lock only the port doing the IO for one file, for example. And we tried to. So we have continued to work on that to making more fine-grained locks and remove locks when possible. So I think we have made optimization to the way locks are made for ETS tables. We still have locks, but they are fewer locks and be optimized.
I
Yeah, I
think
think that.
we're talking. Yeah, we're talking about locks, we're talking about concurrency, we're talking about parallelism. This brings to mind a really great quote by Rob Pike, one of the creators of Go, on parallelism versus concurrency. Concurrency is about dealing with lots of things at once. So it's about how you design and structure your code. Parallelism is about doing lots of things at once. So it's about execution. And so, yeah, and this is where what you've done is you've basically, with multi-core, taken concurrency, which is, the way you designed your code, and made it parallel. And, parallelism is about, being able to execute this concurrency in a very, very efficient way. And yeah, and it's not for the faint of heart.
Erlang is optimized for concurrency, and we can do parallelism for if the task can be performed, can be split into different Erlang processes. In that case, we can run them in parallel to improve performance. Let me just take that sentence. So for parallelism, can work in Erlang if a task to be performed in parallel can be split into different Erlang processes. If you have tiny tasks, it could be more difficult to do parallelism in Erlang.
When you were doing this, what nearly broke? This is the kind of change that can introduce a lot of bugs in your code, which takes years to find.
Yes, I think we did introduce bugs, but for customers, they continue to use, most of them continue to use the non-SMP runtime systems. There was conditional compiling, so you could choose whether you want to have SMP runtime systems. And for the first release, there was not much performance to gain from using SMP runtime system. So that protected us in critical applications that didn't use the SMP runtime system. But others used it, tested, and reported bugs. And we also had a very good tester already at that time, so we ran it and found bugs, and when bugs got reported, okay, we added to test it, fixed the bugs. So yeah, it was manageable.
Parking multi-core, there are other two transitions which are worth touching about in the history of the Beam. The first is that the compiler itself got rewritten in Erlang, and the term representation changed. Why did those two matter?
Let's say term representation, that you have the tag bits, that was changed in order to address a full 4 GB of memory with the 32-bit CPU. That wasn't possible with the old tag scheme. So I think I said because before it was Mikael Pettersson from the Hype team that did that, changed the tag scheme to use a stage tag scheme. So that solved that problem. And regarding the compiler, so it was actually always in Erlang. It has never been written in C or some other language. So the front end for the compiler, the parsing and so on, that was shared with Jam, and I suppose V as well. So we had a special backend for Beam, written by Bogdan. Okay, I can actually show you some slides about the evolution of the compiler. So here is a slide showing here's a slide showing the backend for the original Beam compiler. And there were basically 3 passes in the backend. So it was a compilation to some intermediate code, then some optimization, and then it was converted to Beam files. A little bit later, decided to use Robert's new compiler for V. He wanted to make a new version V with a new compiler. Actually, he never implemented that new V, but we used the compiler. So we had basically these passes in the compiler. So the last pass was to generate V instructions. I adapted it to instead generate Beam instructions. So we can use that architecture for I think we use it for R6, UTP R6. For R7, there was another invention from the Hype team, and also core Erlang intermediate format in the compiler. And I think the original idea came from Rickard Karlsson. But we discussed it, a meeting between the UTP team and the Hype team, and that resulted in a document, the core Erlang language specification. And Robert implemented that in the compiler. So to this day, we use this format core Erlang as an intermediate format. We still do some optimization on that format. For R7, we ended up with this compiler process. So there was translation to the core Erlang format, and there was syscore full, that was core Erlang optimizations, and then it was conversion, pattern matching compilation in V3 kernel, and then generating code, V3 code gen. So I adopted that for Beam. Then I added some additional optimization passes of the result in BEAM code, and then adapted the BEAM RSM path from the original compiler. So this was a new compiler script in OTP R7.
Across all of these, single core to multi-core, the compiler written in Erlang, the term representation changing, is there any one pattern in all of this?
I'm not sure. It's getting better all the time. I'm not really sure.
Backward compatibility, and each transition has gone in and actually removed binding constraints whilst maintaining all of the operational properties, because I think backward compatibility is one of your key strengths and requirements.
Yes, that is a very strong requirement. We try to make it as backward compatible possible. So if you need to do something not backward compatible, we will warn ahead time to 1 or 2 releases before it happens. For example, if you need to remove a BIF or something. Well, and hot code loading, we have to have that working all the time. And another constraint is tracing. You can trace function calls and message calls and so on. And many Erlang projects consider that to be a killer feature of Erlang. So we must have that working even when we implement compiler optimizations. We must not do optimization that are not safe if tracing is being done.
I remember that. I mean, when there are 2 points I wanted to add. One, it comes to actual tracing and debugging. You're able, without trace compiling the code, to create triggers on local variables, so that a trace event is only triggered if certain comparisons on variables of local functions actually match. And this allows you, to have the tracing on production code without affecting performance. So that's an amazing quality of the Beam. But the second is actually when we went in and ported the XD301 from a single core architecture to a multi-core architecture. And I think it was probably 2006, 2007. And not only did they port it, we're talking about 500,000 lines of C and C++, over 2 million lines of Erlang code. It took them 2 weeks to port this code base and get it to run on a new hardware. And this on a new hardware, new virtual machine running on multi-core. So 2 weeks was amazing. It was also a new operating system for that matter. So that was amazing, and just talks to the what you've actually the effort which has gone in ensuring everything's backwards compatible. But what happened back then was, despite they got everything up and running in 2 weeks, then they spent about one person year, chasing new race conditions, which weren't visible in the single core implementation. So there's a new type of bug which appeared, which was that around race conditions. And again, I said one person year here, which in the grand scheme of thing was not much, because at that point in time, I think at least it was 2006. So we're talking about at that point in time, I think the team was about 80 to 100 devs, which have been going on for 7-8 years. It was maybe 1% of the whole effort was to get it running on a multi-core architecture, which isn't much. But to add to that, once they did it, the increase in performance was about from a single core to a dual core machine was about 80-90%. So it was massive. Do things right from the start. You're then able to you get the performance increase with every new core you add. Talking about performance increases, a little disclaimer: we'll be releasing a whole episode on the JIT compiler, just-in-time compiler, next week. So we'll keep this short. In a few words, what is the JIT compiler, and what took so long for the Beam to get one after decades as an interpreter?
There has been 3 or 4 previous attempts to make a JIT, and they were not successful because they wouldn't speed up real Erlang code except for small benchmarks. This attempt is a little bit different. It doesn't try to find hotspots. It will translate all Beam instructions to native code when loading a module. And that approach turned out to be successful because we don't spend time trying to find out hotspots in the program. We just translate everything to native code.
The JIT, right? I mean, adding that in, we're translating code from the traditional Erlang bytecode all the way down into JIT. Did this break portability or hot code reloading? Because now you're changing the whole underlying bytecode. How did that go?
No problem. You can still do hot code reloading, and if you don't have 64-bit system for either x64, x86 64 or ARM 64, you can still use the traditional BEAM emulator. So it's still portable. Everything still works.
Type-based optimizations shipped in 2022. What changed and why does it matter your beyond raw speed?
We did compiler work in UTP 22 to add a new intermediate representation of the code to be able to do more optimizations. And we added a new type analysis pass that could figure out the types. But we found we couldn't really do as many optimization that we would have hoped. So while it did reduce code size, we didn't see that much of speed improvement. When we had the JIT, we realized that we could pass on type information from the compiler to the runtime system. And the runtime system knows much more about the environment there. So the JIT can do many more optimizations. So that was what we started to do in UTP 25. We did the first version of including types in Beam files and letting the JIT do optimization based on that. And we have improved that ever since.
Now, for the listener, the Erlang has no static types, in the compiler. So where do all these types actually come from?
Yeah, so that is the type analysis pass that I talked about. So when, for example, if the compiler sees an expression A plus B, then it can infer that both of these variables must be numbers. If the operation succeeds, then they are numbers. And they're also guards. If the other is integer guard, okay, we know that it is an integer. We have a new is integer guard /3 in UTP 29 to make it easy to also include a range. So just an integer in a certain range. And the compiler will see that and include range information in Beam files. And the JIT can see if you are adding two numbers, and you know that there are small numbers that both fit into a word, a machine word, then you can do the addition, and they will not overflow. So you can remove testing code to handle errors and handle overflow and so on.
And Björn, the most recent chapter, native records, we covered it in our last episode released a month or so ago. Last time we had you on the show. In the arc of the whole Beam's evolution, and for those listeners who haven't listened to the episode yet, where does it sit?
Well, it's more convenient data structure. I think I said it's convenient for debugging. I actually starting to change records in the compiler to use native records, so that will be easier to debug the compiler and print out things. And actually, found some bugs. I think all the merge a fix for that will be included in the next emergency patch. And it will also be better types to be able to find more types with static checking before running the code.
So we can safely say that the Beam is the SMP runtime plus the JIT compiler plus the type-based optimizations that you just mentioned, and now the native records. Is that a pretty fair assessment, or am I just kind of simplifying everything a little bit too much?
Oh, I think that's reasonable. Yeah.
We've traced the pattern. Each transition removed, whatever constraint was binding at the time. Single core to multi-core, interpretation overhead, the type information gap we've just covered. Looking forward, looking at the next 5 to 10 years, or even less than that, just looking forward, what's the next binding constraint you're seeing? What's the next big thing guys are working on, which which you can talk about, which will still ensure everything's backward compatible, and that will then lead to static typing work.
Yes, I think we have some long-term plans, which are just ideas at this stage to further improve performance. And one idea is to have some concept of an application for the compiler. The compiler only sees a single module, but suppose we could make it see an entire application, and then we could also make sure that you can't reload one module in that application without reloading all of the other ones. So if you do that, the compiler can do optimizations across module boundaries. So that is one long-term thing we are thinking of. Another long-term thing is a new beam format that is friendlier to the JIT. So we can let the JIT do some register allocation. Now we still have the X registers for the beam. We still have them either in machine in CPU registers or in RAM. But if we could eliminate them and let the JIT allocate registers, we could generate better native code. But that's of course also long term, 5 or 10 years probably.
Another question is, where do you spend your time worrying about the beam these days? What is it you're specifically doing?
I like to write more optimizations. It's getting harder and harder because we've done all the easy optimizations, but I still like to do more optimizations. For OTP 13 in particular, I will be working more on native records and do optimizations of native records that I talked about last time.
WhatsApp pushed, was there and helped and pushed for native records, and that in part, came out of the static typing work they've been doing. Where is that heading? Will the beam move, towards real static typing?
Yeah, possibly. We are looking at what the projects do, what they're doing in Elixir. There are some other research projects trying to do better type checks. So we definitely looking at that. I think we will move in that direction to add more type checking into the possibly into the compiler to do some more type checking and warn at compile time as Elixir does. That is also a long-term thing.
Okay, actually, we've got Guillaume Duboc and Annette Benusa, coming in one of our, we're recording coming in one of our future shows where we will be discussing the type system. So it will be interesting also to hear what they're saying and some of the work they're doing and how it's going to be integrated. You teased this in the beginning, so did we. So the Beam isn't only virtual machine. We've got the Atom VM on microcontrollers, Ling, so the Erlang on Zen hypervisor, which was running on the bare metal, which you could fire off in a few milliseconds. Does the future of Erlang get more fragmented, or does the Beam remain the center of gravity?
I think that Beam will be the main virtual machine that most people will be running Erlang on, but I think for certain applications, other are better suited. If you have a really small memory, RAM, Atom is a better choice, or could be the only choice.
Beam is being constantly worked on, and you're basically what you've been doing is removing constraint after constraint. Now, is the Beam ever actually done? Is there going to be a point where you're saying, okay, we don't know what's the next thing to kind of optimize or what's the next thing to do?
Probably not. That would be boring if it was finished.
Now, for the listeners at home, if there's something that you want them to really, remember about this episode and to kind of take it, take into heart and really, maybe if you see them at the next conference, what would you want them to really remember about this whole episode?
I suppose that remember that we're always working, trying to make the beam better, to have better performance in all ways that we can optimize it.
Anything else you'd like to add, Björn, before we wrap up? This was a very insightful conversation. Thank you for that.
I've done some presentation called My Beam History at the EU Elixir conference and then at Code Beam Light Stockholm last year. And they are available on YouTube. And I suppose you can link to them. So if you want a lot of more details about what I've been talking about, digging deep into the loader and so on, you can watch one of those presentations.
Here, I'm actually sharing the ElixirConf EU talk you gave. You can find it on YouTube, but I was there. It was really, really interesting. Thanks for suggesting it, Björn. I mean, just to wrap up, I think when Björn and I started at Ericsson, there were three people, each building their own virtual machine. And to point out, it wasn't a race. It wasn't may the best one win, but it was a way to learn and share the best ideas which solved real world problems and actually worked in production. That was kind of the cooperative environment of the lab as we saw it. So 30 years on, there is one of them which is running a meaningful slice of the world's telecommunications, messaging, online gamings, and payment solutions. And I think one of the key people in the team which built it has spent those 3 decades, very, very quietly, making sure it got faster without ever breaking things, that made it worth running. And in fact, I believe, Björn, that the conference talk you suggested, so My Beam History, was the very first conference talk you ever gave. Is that right?
It was the second, actually. I did one on
The
the
second
new feature called native code coverage in Berlin.
in Berlin.
And yeah, it
Okay,
was,
that's right. That's right. Yeah,
yeah.
it was your second talk, so in 30 years, which is great. It was great to have you on stage. So and so you kept on working with all of this for 3 decades, fairly quietly, with the exception of two conference talks in the last few years. And you made sure it went faster, and you made sure it never broke backward compatibility. And this is why the beam is still there where it is today. So if you're new to the whole Erlang ecosystem, that's and to this podcast, this is what the beam there done that podcast does. We get the people who've built the foundations. The rest of us still standing on the shoulders of giants. So please hit subscribe. As we've got an episode on the JIT compiler coming next week. We've got one soon after on the type systems, and we're hoping to schedule one on the different Erlang machines in the making. Historical ones and new ones in the making. So, thank you all for listening. And just for the record, this episode was recorded May 26, 2026.